Most of the rotary kilns are equipped with floating tires. These steel rings have a loose fit with a kiln shell to allow thermal expansion. Therefore, it is crucial to monitor the tire play. This prevents damage to the kiln shell and the refractory bricks. The outer diameter of the shell is slightly smaller than the inner diameter of the tires. The resulting play is called tire clearance. It forms a gap at the top of the kiln. As the shell is closer to the heat inside the kiln than the tires, it will get hotter and therefore expand more and faster than the tires. Especially during the kiln heating phase, the clearance can become critically low, which brings the risk for constricting the shell. This means that the kiln gets locked up in the tire, which is hindering any further expansion of the shell. On the other hand, when the clearance becomes too large, the gap at the top of the kiln widens, affecting the shell's roundness. This elastic deformation is called ovality. Ovality also occurs at the areas where the tires are supported by the rollers. Despite their large thickness, the tires deflect slightly under the weight of the kiln. Due to the kiln rotation, the deflection coming from the ovality is cyclic and affects the whole circumference of the kiln. In the tire area, mainly at the 2 and 10 o'clock positions, the pressure between the bricks increases, and at the 12 o'clock position, the pressure is reduced. This cyclic load change has a negative impact on the refractory bricks. They might become loose or break. The ovality is measured by the Ovality Sensor to understand if the bricks are at risk. The Ovality Sensor is attached to the kiln shell close to the tire while the kiln is in operation. This sensor measures the cyclic deflection during a full kiln turn. The values are transferred via Bluetooth and displayed on a PC screen. The tire clearance not only causes ovality but also relative movement between the tires and the kiln shell. This is called tire creep or migration and means that the shell, which is rolling inside the tire, completes a full turn a little bit faster than the tire. The creep can be measured. The simplest method is by making a mark on the shell and the tire while the kiln is rotating. After a turn, the marks will be offset by the amount of the creep. For example, a tire lags 18 mm behind the shell after a kiln turn. This means the creep is 18 mm per revolution, and the difference in circumference between the tire and the shell is also 18 mm. By dividing the creep by pi, we know the clearance. In this example, it is roughly 6 mm. Let's imagine there would be no ovality, so the kiln shell and the tire remain perfectly round. In this scenario, the gap at the top is equivalent to the clearance. But due to ovality, the shell flattens a bit at the top and the gap becomes slightly bigger. How much bigger depends on the load and the shell thickness. In the next example, the creep is 35 mm per revolution, which leads to a top gap of approximately 15 mm. Here can be seen the ovality is high and has a negative impact on the refractory bricks. Another method to measure creep is by attaching a pencil to the shell and a paperboard to the tire by magnets. The pencil draws U-shaped curves on the board. The height represents the top gap and the width represents the creep. Nowadays, with increasing kiln speeds and greater safety awareness, these manual methods are no longer recommended and have been replaced by automatic systems. The first automatic systems were based on mechanical switches. However, the mechanical switches are not reliable and have a short lifetime due to the high number of cycles and the hot environment. A better option are heat-resistant inductive sensors. They do not wear out and therefore have a long lifetime. But two disadvantages still remain. First, mechanical switches as well as the inductive sensors are not precise. Sometimes the signal comes a bit earlier and sometimes a bit later. To account for this inconsistency, the creep values must be averaged over 10 to 20 revolutions to obtain a stable signal, which causes undesirable delay. The second problem is that any change in kiln speed affects the readings, meaning accurate values are only possible when the kiln speed remains constant. The lack of accurate creep values is especially critical during the heating phase, when the kiln stops every quarter or half turn. To provide precise and reliable information about the tire clearance, the creep monitor was developed. It works even during the heating phase when the risk of locking the tire is the highest. Unlike conventional systems, this setup tracks kiln rotation directly from the girth gear. An inductive sensor mounted in front of the gear emits a pulse for each tooth as it passes. The controller converts the teeth count into millimeter values, which start at 0 and end at the shell circumference after each kiln turn. This setup can be seen as a very large rotary encoder, which makes the measurement precise, stable, and independent from the kiln speed. To measure the rotation of the tires, a precise heat-resistant optical sensor was developed. One tire sensor is installed next to each tire. For safety, it is positioned slightly offset towards the in-running side to keep the space under the tire clear. A heat-resistant magnet with a rod is attached to the side face of the tire and acts as a switch flag. When the switch flag is passing the sensor, a pulse is generated and sent to the controller of the creep monitor. This setup makes it possible to get consistent creep values, also when the kiln is stopped periodically during the heating phase. The millimeter value is recorded at the moment when the signal from the tire sensor is received. When the switch flag passes again, the next millimeter value is recorded. The difference between two consecutive values equals the tire creep. In this example, the creep is 18 millimeters per revolution, which is a good value, where the ovality is still small. In case there is no longer any gap present between the shell and the tire, successive millimeter readings will remain the same, indicating zero creep. Zero creep poses a risk of shell constriction, as the tire inhibits any further thermal expansion of the shell. On the other hand, when creep exceeds 30 millimeters per revolution, ovality also increases, reducing the refractory's lifetime. To reduce the ovality, the tire clearance and the creep, shim plates are added under the tire pads. In case the creep is too low, the shim thickness needs to be reduced. As the tire clearance varies with the shell temperature, it is important to consider the creep values over several months to calculate the required shim thickness. That is why a reliable creep monitor is essential to avoid major issues with the refractory and the kiln shell.